So today we will discuss about bending stress and shear stress in beams, module 3 in the syllabus. So we have learnt about bending moment and shear force, and also how to draw the BM and SFD in the earlier classes. Now, to understand about bending stress and shear stress, first we will take up bending stress. I will consider a simply supported beam AB subjected to some loadings, concentrated load or UDL, whatever it is. Due to that, what happens, the axis of the beam, initial axis of the beam, it bends like this. So this curve is called as the deflected curve. So there is no deflection at the support because reactions develop at the supports. Those reactions, they resist the deflection at the supports, but at all the other points, so you will be having deflections. So the deflection will be due to the development of bending moment. So you can see that in the case of simply supported beam, sagging bending moment takes place like this. So due to that, the axis is gets shifted like this. Now I have shown that in another diagram here. I will consider a particular length of the beam CD, and due to that bending, what happens, that CD will be contracted above that initial axis, and it will be elongated below the initial axis. You can see here. So whatever layers are there above the CD, it gets contracted. So that is why I have written here contraction. That because of contraction, there develops a compressive stress. So that compressive stress is called as bending compressive stress. Below this CD, there will be expansion or elongation of the layers. So because of that elongation, there develops a bending tensile stress. So that means this CD portion, whatever is there, it neither elongates nor it compresses. That means this length remains same, CD length remains same, whereas above CD, the layers gets contracted, below the CD, layers get elongated. So because of that, bending compressive stress will develop above this CD, and bending tensile stress will develop below this CD. So this layer where there is neither compressive stress nor tensile stress, it is not subjected to any stress. So that layer is called as the neutral layer, NL. Along the length of the beam, this layer is called as neutral layer. Whereas if you take the cross section of the beam, suppose if it is rectangular like this with B and D as the dimensions, so if you cut this, you can see like this. You can see that the centroid of this cross section will be here, exactly at the geometrical center. And if you draw a horizontal line, that line is called, passing through the D is called as the neutral axis. So at the neutral axis, also your bending stress value will be 0. So bending stress is denoted by small f. So bending stress value will be 0 at the neutral axis. See, neutral layer and neutral axis, they are mutually perpendicular to each other. Along the length of the beam, it is called as neutral layer. Perpendicular to the beam, the cross section, it is called as neutral axis. So both at neutral axis as well as at the neutral layer, you don't have any bending stress. So that is very important point because it neither elongates nor contracts. Now, in the case of a cantilever beam, what happens? This is simple supported. In the case of cantilever beam, so the deflection will be hogging in nature like this. So if I take a cantilever beam like this, if it is subjected to some load like this, definitely what happens, this axis will be deflected in hogging fashion. That means like this. So in this case, what happens, if you take the cross section of this cantilever beam as rectangular cross section, if you locate the neutral axis, it passes through the centroid. Above the neutral axis, you see tension. Below the neutral axis, you see compression because of the opposite nature of bending moment. So in the case of cantilever beam, it is subjected to hogging bending moment, whereas in the case of simply supported beam, it is subjected to sagging bending moment. Here it is sagging. So only the nature will be different. So that means, in other words, we can say, in the case of simply supported beam, the layers which are above this neutral axis, they are subjected to compressive bending stress, that is FC, whereas below the neutral axis, it is subjected to tensile bending stress. Whereas in this case, it is opposite. Above the neutral axis, it is subjected to tension or tensile bending stress Ft. Below the neutral axis, it is subjected to compression bending stress Fc. That's all the difference between the nature in simply supported and cantilever beams. So in other words, what we can say is, whenever the beam is subjected to some external loads, bending moment develops, shear force develops. The bending moment due to the effect of the bending moment and shear force is deflection. So during that time, stresses will develop. Those stresses are called as bending stresses. Of course, shear stress also will develop, but compared to bending stress, shear stress magnitude is very less. So that is the major portion of the stress develops due to bending moment effect. And in the case of simply supported beam, the layers above the neutral axis, they are subjected to compressive bending stress, whereas the layers below the neutral axis, they are subjected to tensile bending stress, and in cantilever beam, it is reversed. Now, the next concept is, what do you mean by pure bending? So that means only bending moment should be there should not be any other force. So only bending stress should be there. There cannot be any other type of stress. That is the concept of pure bending. Only bending stress should be there. So for example, I will take a simply supported beam like this, A and B, carrying two concentrated loads W at equal distances. That means this beam is symmetrically loaded beam. So symmetrically loaded beam. In the case of symmetrically loaded beam, reactions are equal. So total load is 2W. Reactions are equal, therefore each reaction will be W and W. If you plot the bending moment diagram for this beam, so you will get like this. This is the bending moment diagram. So at C you have bending moment of W into L by 3. At D also you have bending moment of W into L by 3. Both are positive because upward forces give positive bending moment. That's tension, friction, tension. So sagging bending moment will be there. If you plot the bending moment diagram, at A it is 0, at B it is 0. At C and D it is equal to WL by 3. That is constant. And join that by a straight line, because for concentrated load, bending moment diagram profile is a straight line. So this is bending moment diagram. If you draw the shear force diagram, at point A, shear force is plus W. From A to C there is no force, so horizontal. Then at C, come down by W. From C to D there is no force, horizontal. From at D you have a downward force of W, come down by W. No force from D to B, horizontal. At B you have a reaction W upwards. Now here, this is positive, this is negative. Now if you observe, two things are there here. In bending moment diagram, you have constant bending moment from C to D, which is equal to WL by 3. And in the same region C to D, shear force is 0. It is neither positive nor negative, it is 0 shear force. So that means the portion CD has got constant bending moment, also 0 shear force. That portion is called as, we said that it is subjected to pure bending. Because it is subjected to only bending moment, there is no shear force. And that bending moment also is constant. So this portion of the beam AB is called as, this portion of CD portion of the beam AB, we say that it is subjected to pure bending, or in other words, simple bending. So the simple bending means, or pure bending means, the portion of the beam should be subjected to only bending stress and there is no other type of stress there. That is the meaning. Now we have one important equation called pure bending equation. So I have given the equation here, M by I is equal to F max by Y max is equal to E by R. You have to remember this equation, pure bending equation. Here M is called as the moment of resistance of the section of the beam. So section means it can be a cross section, that is rectangle, or it can be circular, or it can be D section, I section, whatever it is given in the problem. So moment of resistance of that particular section, normally we take that equal to maximum bending moment, because whenever you are designing any structural member, so the moment carrying capacity of the section should be greater than or equal to maximum bending moment. Otherwise the section will fail, member will fail. So what we do is in problems, we take this moment of resistance of the section equal to maximum bending moment whatever occurs on the beam. Next, I is called the moment of inertia, Mi, of the section above the neutral axis. So above this neutral axis, we have to find out the moment of inertia. For example, for a rectangular section, so your IME anything is nothing but Ig only. Moment of inertia about the centroid is the same as moment of inertia about the neutral axis. In the case of a rectangular section, the formula is BdQ by 1. So like that, we have to find out the moment of inertia if T section, I section are given. So that is that will be in millimeter power 4. You can see here bending moment will be in kilonewton meter, or you can express that into Newton millimeter. That means 1 kilonewton meter is 10 power 6 Newton millimeter. So you should be very careful about units here. So everything, all the units, you have to convert it into newtons and millimeters before substituting in the formula, in this formula. Next, F max is the maximum bending stress. So maximum bending stress unit is Newton per millimeter square. So that maximum bending stress, it can be either tensile or it can be compressive. Y max is the distance of farthest fiber from the neutral axis. This you have to understand. Farthest fiber means this is the always distance is measured from the neutral axis, above the neutral axis or below the neutral axis. So farthest means, so for example here in the case of rectangular cross section, this itself is the farthest layer. Here also this itself is the farthest layer. Your Y max is same here. So in the case of symmetrical sections, Y max will be same on either side. On either side. That's what I have shown here. Here you can see here FC max I have written. FC max is the stress developed here. FT max is the stress developed here. This is T stands for tension, C stands for compression. In the case of a symmetrical section, both will be equal. FC max will be equal to FT max. Next, E is called as the Young's modulus of the material of the beam. It may be RC beam or steel beam, whatever it is. Young's modulus of that material, which is once again expressed in MPa or Newton per mm square. Then R is the radius of curvature of the deflected curve. So this is the deflected shape. So you have an imaginary radius of center of curvature will be there. The distance from center of curvature to the deflected shape is your R, which is expressed in millimeters. So these are the units you have to follow. M in Newton millimeter, I in millimeter power 4, F max in Newton per mm square, Y max in millimeter, E in Newton per mm square, and R in millimeters. So if you observe this equation, you can see here. If you want F max is equal to M by I into Y max. M by I into Y max. So this M by I is constant for a given section. I is constant, maximum bending moment is also constant. So M by I becomes a constant. That means we can say F max varies directly with Y max. As Y max increases, Y increases, your F max also will get increased. That means you can say F directly varies as Y. You can say here there is some constant here, that is F max is equal to M by I into Y max. That means there is some constant, so constant into Y max you can say. So F is directly proportional to Y. As you take these layers, at neutral axis it is 0, F is 0. If you take some layer here, at this level the value of F is this. Then if you take a layer here, from here to here this is your Y, and the value of F is this. So these are all F values. Please note, and these are all I values. Y values. Y is measured from the neutral axis. As Y increases from the neutral axis, your F value also increases. And since it is a constant, this represents straight line here. F is nothing but one value. Y max is another value, like X and Y. So if you take this as Y, this as X, Y is equal to K into X. Y is equal to K into X is a straight line equation. Therefore, if you join the points, that bending stress diagram, so this is called as a bending stress diagram. So this bending stress diagram is a straight line. Bending stress diagram is a straight line. Let's take bending moment diagram. Here it is bending stress diagram. The thing is, the difference between bending moment diagram and bending stress diagram is that bending moment diagram is written for the entire length of the beam, whereas bending stress diagram is written at a particular section of the beam. At a particular section, if you take a section here, I am going to take, so bending stress diagram is written for a particular section of the beam, whereas bending moment diagram is written for the entire length of the beam. So what I mean to say here is bending stress varies linearly with the distance from the neutral axis. So that is called as linear variation. And another point is flexural rigidity. This is another term which you have to understand. Flexural rigidity is nothing but the product of Young's modulus and moment of inertia about the neutral axis E into I. So E is expressed in Newton per meter square into I is expressed in millimeter power 4. So if you simplify that, you will get Newton millimeter square, or you can write in kilonewton meter square also. Just like you have axial rigidity, flexural rigidity. The axial rigidity means A into E. So cross sectional area into Young's modulus, product of A into E is called as axial rigidity, whereas product of Young's modulus and moment of inertia is called as flexural rigidity. Okay.